All right, good morning. What we're going to do today, let's see, last time we've gone through the mechanics of breathing, we've gone through kind of all the parts, we've gone through partial pressure. So what do we look at today? It's kind of going to be a list of numbers with a couple of important kind of concepts squeezed in. We're going to look at the concentration of the respiratory gases, oxygen and CO2, in several different places. The atmosphere, the lungs, arterial blood, the tissues, venous blood, back to the lungs. We'll do oxygen first, and then we'll do CO2. I just make a table. That's what I'm going to do on the board here. And then at the end, I'll stick in a prettier picture that kind of shows the locations, but it's not a big deal. So all these units are going to be in partial pressure. So let's start with, I'll just use ATM. That's not automatic teller machine, that's atmospheric abbreviation. All right, we've already mentioned, the atmosphere at sea level, pressure is 760 millimeters of mercury. Percent concentration is 21% for oxygen, so you multiply them together to get the partial pressure. So PO2, 159, all the units will be millimeters of mercury. All right, so we have atmospheric air. It has a partial pressure of oxygen, at sea level, about 159. Now, we inhale out. Just suck it in our external nares through the nasal cavities, trachea, down into the alveoli of the lungs. If we measure the concentration of oxygen in the alveoli, it's about 104 millimeters of mercury. That's kind of the average value if you took a sample of gas out of the alveoli. Now, a couple things to note about this right off the bat. This is a huge drop. I mean, just by inhaling the air, we've lost a third of the available oxygen. That's pretty bad. Why is it like that? Because it turns out mammal respiratory systems, including humans, they suck, literally and figuratively. They're very inefficient. So, when we breathe in this air, that is a huge drop. Again, it doesn't matter because atmospheric air has so much oxygen. We haven't evolved to have a very efficient respiratory system. We're not like a fish or a bird. Theirs are a little better. Part of the reason for that drop is we have what they call tidal breathing. The air goes in and out the same hole. So we inhale air, typical tidal volume is about half a liter, 500 mLs. You're stuffing that into a lung that holds maybe 6 liters. Most of the air that's already in your lungs, it's old, it's stale, the oxygen is already diffused out. So you're bringing in a little new fresh air, and you mix it with all the old stale air in the alveoli. That's partly what causes this drop. Some other things to factor in, water vapor. Remember, when you inhale through the nasal cavities, one of the things the nasal cavities do will humidify the air. Well, that's adding water vapor. Water vapor is a gas, it exerts a partial pressure. Behaves a little differently. The partial pressure of water vapor at body temperature, if the air is 100% relative humidity, it's 47 millimeters of mercury. But the atmospheric air is not saturated with water vapor. So when you bring that in, adding that water vapor basically dilutes or displaces some of the oxygen. So we drop a little bit. Now, in the lungs, diffusion is very efficient. You basically reach equilibrium with the air in your lungs and the blood going through the pulmonary capillaries. However, you'll usually see, and I'll put blood, arterial, art. "95 millimeters of mercury is about the partial pressure of oxygen in your arterial blood. That is the blood leaving the pulmonary capillaries. Yes, technically it's in the pulmonary veins, but then it's going to go down to the left heart and it'll be in the arteries. So this is usually referred to as arterial oxygen concentrations. That's not the same. 95 is not 104. That's not because of inefficiencies in diffusion. That's because of inefficiencies in ventilation perfusion matching. Talked about that earlier. Well, we normally try to move the air to the same spot in the lungs where we're moving the blood. It's not 100%. You do have some what they call physiological dead space. There are some areas of the lungs that may not be perfused, or that are perfused but not ventilated. So some of the blood still reaches equilibrium with the air in those alveoli, but because they're not ventilated, the O2 levels are much lower. You mix all that blood together when it comes out of the pulmonary capillaries, so you see a slight drop. It's not that significant, but that's because of some mismatch in the ventilation and perfusion coupling. So this is arterial blood. It's going to travel to the tissues. And now, once we get to the tissues, a second set of capillary beds, the systemic capillaries. This, again, is going to allow oxygen to diffuse out, because, again, the source, or the place where you're using the oxygen, the sink, I guess I should say, not the source, is the tissues. They're using this oxygen in those metabolic pathways. Oxygen is a final electron acceptor when you're breaking down things like carbohydrates and other nutrient molecules. So as the blood moves through the tissue capillaries, it does reach equilibrium. And so PO2 in the tissues, that is, if you took a sample of tissue fluid, pull it out, analyze it for PO2, it's going to average about 40 millimeters of mercury. Now that's an average. Different tissues will have different metabolic rates. Some tissues, the PO2 will be lower, some higher, depends on their activity. But if you pull it all together, on average, that's what's draining out of the tissues. The blood, as it moves through these tissues, it does reach equilibrium. So if you sample a blood after it's passed through the tissue capillaries, we'll call that venous blood. It's kind of the used blood. It's already passed through the tissues. The oxygen is diffused out. It does reach equilibrium. Venous blood, about 40 millimeters of mercury. That's what's going to come back, say, through the vena cavas, back to the heart, and that's what's going to go back to the lungs. Those are the partial pressures, basically, as we go through the system. Now, one thing I want you to note, PO2 in the alveoli, that's your source of your oxygen, once we're in the system here, in the circulatory system, 104. PO2 in the blood coming back to the lungs, that is in the pulmonary arteries, just before they get into the pulmonary capillaries, is 40, which means, I'm going to put delta PO2. The concentration gradient, sort of pushing oxygen from the alveoli into the blood, this minus this, that's going to give you a difference of about, 64 millimeters of mercury. That's a partial pressure difference between the blood coming into the pulmonary capillaries and the air in the alveoli. So that is a concentration gradient. That's what's pushing the oxygen into the blood. The difference in PO2 is 64. Remember that, because I'm going to come back to it. Now, quickly, let's look at CO2. CO2. Trying to give myself enough room here. I need to be taller. All right, PCO2, it's a gas. You can measure its partial pressure. Of course, in the atmosphere, there isn't much carbon dioxide in the atmosphere. It's very low concentration. It's 0.04%, somewhere like that. If you measure its partial pressure of CO2 in the atmosphere is like 0.3 millimeters of mercury. That's hard to see. It isn't writing well up there, but it's 0.3 millimeters of mercury. That's the partial pressure of CO2 in a typical open atmosphere. It's not very much, pretty insignificant. Now, when you inhale, immediately when you inhale, the PCO2 in the alveoli (40 millimeters of mercury). It's huge. As we'll see a bit later, our respiratory system actually functions to retain CO2. We have a tremendous amount of CO2 in our lungs and in our blood. Now, as the blood passes through the lungs, that blood is going to reach equilibrium. So arterial blood also has a PCO2 of about 40 millimeters of mercury. So it reaches equilibrium there. Now, when you get to the tissues, tissues are the source for the carbon dioxide. This is where you're producing it. Again, I'll write the equation for the metabolic pathways up in a minute. But CO2 is produced in those metabolic pathways. It's end result of the matrix reactions of cell respiration. So tissue PCO2 is going to be the highest, about 46 millimeters of mercury. So if you pull a sample of fluid, extracellular fluid around the tissues, metabolically active tissues, PCO2 will be about 46. It's a little higher than it is in the blood. So when the blood passes through the tissue capillaries, of course, diffusion will occur. It's the opposite direction of oxygen. PCO2 is higher in the tissues, lower in the blood, so it will diffuse out. And so the venous blood will have a PCO2 that's about the same as it is in the tissues, 46 millimeters of mercury. Again, that's an average. And that is the blood that will return to the lungs. So if we look at the concentration gradient or difference moving CO2 out. So I'll do delta PCO2. So this is a concentration gradient allowing carbon dioxide to fuse from the pulmonary capillaries into the alveoli so you can exhale it. We got 46 for the blood coming into the pulmonary capillaries, that's your venous blood. We got 40 in the alveoli, so it's only 6 millimeters of mercury. Not nearly as high as oxygen. Oxygen got 10 times more of a concentration gradient. Now, one of the things, know these numbers a little bit. I'll pop them up there in a multiple choice somewhere. But look at these differences in concentration. If you just had to guess, which do you think you diffuse more of? Oxygen or CO2 over, a minute of time or 5 minutes of time? All else being equal, surface area is the same, distance the same, that sort of thing. You've got 10 times the concentration gradient for oxygen than you do CO2. So you might be thinking, well, that means I'm going to diffuse a whole lot more oxygen into my blood than CO2 out. Well, it turns out, no. They're basically the same. That is for every molecule of oxygen that goes in, about a molecule of CO2 goes out. There's a few details you got to look at there. Depends on what you're eating a bit. If you're eating all carbohydrates, it will be 1-1, but we don't eat all carbohydrates. So how do we explain this? Again, I'm going to write down that equation for cell respiration. Let's see, what was that? That was C6H12O6. That's glucose. Plus 6O2. Remember, we need those oxygens in the mitochondria. That is going to end up producing 6CO2 plus 6H2O. That was our net equation for cell respiration. And of course, we ended up using that energy to assemble like 38 ATP, something like that, depending on how you do your bookkeeping. But that's kind of our overall net equation for cell respiration. What I want you to note is if you consume 6 oxygen molecules, assuming you're eating carbohydrates, you'll produce 6 CO2s. It's 1-to-1. That's kind of what I mean by you have to move the same amount of oxygen into the blood as CO2 out. How can we, fix that? When we look at this concentration gradient, we should be using or moving a lot more oxygen. I'll use this to introduce the last of sort of the gas laws that you need to keep in mind. Again, we're looking at these qualitatively, not quantitatively, but when you look at how much of a gas goes into solution, it's not just about concentration gradient. Let me see if I can get myself a little room here. A couple of boxes. All right, here's what I'm going to do. Let's say, can we see all the way over here? Yes. I'm going to get a bottle. This is like a compressed gas tank. You get welding supply or something. It's a bottle of 100% oxygen. And I'm going to connect that to a small aquarium, basically a box, an airtight box. And what I'm going to do, you see that okay? It'll do. I'm going to half fill this full of water. Water is basically like plasma. We ignore the blood cells for now. Just, it's the plasma in the blood. And then I'm going to connect this gas tank to this aquarium. And what I'm going to do, initially there's no oxygen in there. PO2 is 0, PO2 is 0 in the water as well. I'm going to introduce oxygen until the PO2 equals 100 millimeters of mercury. So this gas space up here now has oxygen in it at 100 millimeters of mercury. Initially, there's no oxygen in the water. So oxygen will move following its partial pressure gradient from very high partial pressure to low. And so the oxygen will diffuse into the water. Imagine those 10 circles represent the oxygen molecules. Now eventually, you will reach partial pressure equilibrium. If you let it sit there a while, eventually you'll have a PO2 of 100 in the water as well. And a PO2 in the gas of 100. So that's equal partial pressure, but does that mean there's an equal number of molecules in this half of the box, which is 100% oxygen, versus this part of the box, which has a lot of water in it, which takes up a lot of space? The answer, it's probably a little intuitive, no. There's way more oxygen molecules up here compared to down here. The partial pressure is the same, the content is not. Because there's one other thing you have to factor in. When you look at how much of a gas will go into solution, this is Henry's law, I think they'll describe it in your textbook. You got two things to worry about. One is the partial pressure gradient. Partial pressure is important. Again, that's what's driving the oxygen into the water, high partial pressure to low. But then the amount that actually gets into the water is also determined by solubility. Gases, like solids, like salt, sugar, calcium carbonate, things have different solubilities in different solvents. Gases are the same way. Now, solubility is complicated. It's affected by a lot of things. Temperature, the composition of the fluid, concentration gradients, the works. So just to keep it simple, I'm just going to say oxygen has a relatively low solubility. That is, just like salt. If you put a bunch of salt in water, can you keep putting the salt in? Does it keep dissolving, Pour another teaspoon of salt, another. Will it keep dissolving forever? No. Eventually you reach what they call a saturated solution. No more sodium chloride will dissolve into the water. In fact, if any more sodium chloride dissolves, it starts to precipitate out as crystals. You've loaded up the liquid with as much sodium chloride as you can. Same is true with oxygen. When you reach equilibrium, what that means is, yes, oxygen can continue to diffuse into the water, but as fast as oxygen diffuses in, an oxygen molecule will diffuse out. Again, it's that equilibrium thing. But oxygen has such a low solubility, it actually requires very few oxygen molecules to dissolve into that water before you reach equal partial pressure. So the content of oxygen down here is actually quite low. Let me contrast that with CO2, just as a comparison, since we're not really sticking numbers on these things. I'm going to take another container. Here's another gas bottle. This one has CO2. And I'll make another box, same size, all the same characteristics. And I'm going to hook the CO2 tank up here. I'll half fill it with water, just like before. And I'm going to introduce carbon dioxide until the PCO2 equals 100 millimeters of mercury. Just like up here, except it's CO2. Now, just like before, the carbon dioxide will dissolve into the fluid until the PCO2 in the water is the same as it is in the gas phase. But the difference is, just for comparison, carbon dioxide is about 20 times more soluble in plasma than oxygen. Now, what does that mean? If these little blue circles represent oxygen molecules, I've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, I think 10 of them. Everything else is the same. Volume's the same, partial pressure is the same, except it's CO2 with 20 times more solubility. So by the time we reach equilibrium with the CO2 in the air here, what you'd have is, let me draw in some CO2 molecules. These would represent CO2. I'll do dots rather than circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 40, 50, 60, lost it. 80, 90, 100, 10, 20, 30, 40, 50, all right, and so on. 200. Basically, if I had 10 oxygen molecules in here, this is 20 times more soluble. 20 times 10 would be about 200. So I may have 200 CO2 molecules in this volume of water at the same partial pressure gradient. With oxygen, I only had 10 molecules. CO2 has a really high solubility. It's actually really easy to move CO2 compared to oxygen. So back to this. Why the concentration gradient is so different? Because of oxygen's really low solubility. In order to move the same amount of oxygen as carbon dioxide, I have to have a much higher concentration gradient. So that's why there's a difference. Doesn't mean I move a lot more oxygen. I move about the same amount of oxygen molecules as CO2 molecules, but because of oxygen's very low solubility, I have to maintain a much higher concentration gradient. All right, that's Henry's law in a nutshell. What determines how much of a gas goes into solution? 1, partial pressure. 2, solubility. Now, I'll put up a little prettier diagram, but it's going to be the same jump. This is the one that's on the PowerPoint. Back in a minute. All righty. This is that diagram off your PowerPoint. It's more or less the same thing we just looked at. They're just giving you all the boxes here. So this represents atmospheric air. There's your PO2 159, your PCO2 about 0.3. You inhale that air. This is alveolar gas concentrations. Again, PO2 104. PCO2 40. Then we get down into the arterial blood. Admittedly, this is a pulmonary vein, but it's the same as the arterial blood. That one's hard to sample. You don't usually get pulmonary vein samples. If you look at the oxygenated blood, this is systemic arterial blood, PO2 95, PCO2 is 40. Then this is representing capillary bed in the tissues. Again, this is where exchange occurs. That's why you get the color change. Oxygen is diffusing out. CO2 is diffusing in. That's why it's blue at the venous end. But again, in the tissues, PO2 is, it should say 46. I can't read it on this. PO2 is 40, I'm sorry. PCO2 is 46. Can't tell if it's 46 or 45. So in the tissues, PO2, 40 millimeters of mercury. So it's lower in the tissues than in the arterial blood. Oxygen diffuses out. PCO2 in the tissues, about 46. PCO2 in the arterial blood coming in is only 40. So there's a concentration gradient allowing CO2 to diffuse in. We take that blood back to the lungs. This is your venous blood. And then exchange occurs again. The CO2 will diffuse out because there's a 6 millimeter of mercury concentration gradient, 46 versus 40. And the O2 diffuses in because there's a concentration gradient, 104 in the alveoli and 40 in the venous blood. So these have all the numbers if you need to kind of review them real quick. And again, the reason for the huge difference in concentration for oxygen and CO2 at the exchange surfaces of the lungs is because of carbon dioxide's very high solubility relative to oxygen. All right, take care.